Alright guys, welcome back. We're now on topic 3 notes. We're finishing up our unit on atomic structure and we're looking at the periodic table and periodic trends. So in our expected section, we are justifying an atom's reactivity on valence electrons and nuclear charge according to Coulomb's law. So we're going to review what we looked at with Coulomb's law in our virtual lab. We're going to describe an element's location in the periodic table and what it tells you about its properties and structure. So Coulomb's law, which we looked at in our virtual lab, it is force, or we're looking at the force of attraction between oppositely charged particles. Those are going to be our protons and electrons. It's measured in newtons, which we represent with a big capital N. And so there's an equation for it. We're not going to look at it, but it relates the charge, these Q's, to the radius or the distance between them and the force that is exerted between them. And there's a relationship between all those variables that we're going to look at based on what you did with those little fighters in the virtual lab yesterday. Oops. So the two periodic trends that we are going to look at, there is a couple other periodic trends that if you go on to a higher energy or higher chemistry class you'll look at, but the two we're going to focus on are ionization energy and atomic radius. So ionization energy is the energy required to remove a valence electron. If we remember from our previous topic, valence electrons are going to be those outermost energy electrons, and those are going to be the ones that do the bonding and interacting, which we'll talk about in our next unit. Atomic radius is simply the size of the atom. So radius, similar to math, we're looking at from the center of the nucleus to the outermost electrons. So that is our radius. We're looking at distance in that case, or how big that atom is, which relates to how it bonds and forms chemicals as well. So what is the relationship between distance and Coulombic force? And we looked at this in our virtual lab. If we look at this model 1, we're looking at A, B, and C. Between A, B, and C, what we're changing is the distance. As we increase the distance, what does it look like is happening to our force? It's decreasing. So as distance of the particles increases, the force decreases. It's kind of like a magnet. As I pull magnets further away from each other, the force of attraction between those two magnets decreases over time. So this periodic trend, as I go down a column, if I look at this other model here, I'm looking at lithium, sodium, and potassium. And if you look at your periodic table, they are on top of each other in that far left column. So as I go down a column, I can see that those outermost electrons are getting further away from the nucleus. So according to this trend, if I'm increasing the distance, the force is decreasing. And so the distance between the electrons is getting bigger, and that results in a smaller Coulombic force. And this results in two different aspects of this trend. The atom gets bigger, so notice potassium is much bigger than lithium, and the ionization energy gets smaller. So the further away you are, the less energy is required to remove that electron. The closer that electron is to the center of the nucleus, those protons are going to pull really hard on that electron. It's going to be harder to get that electron to go away. And so we can represent that on our periodic table. So if we look at going up or down the column, as I go down the column on the periodic table, atomic radius increases. As I go up the column, ionization energy increases. I like to talk about increasing for all things. A lot of times you'll see these trends on periodic tables where one says increasing, one says decreasing, and I find that that's confusing. And so that's why I've created this graphic or visual for you. And so as we go up and down a column on the periodic table, we are looking at the distance. So distance, how are those distances changing? As I go down the column, my distance is getting larger, which is going to have an inverse effect on atomic radius and ionization energy. Next up, we're going to look at the relationship between charge and Coulombic force. So those two different variables in force were distance and charge, and so now we're looking at charge. If we look at the model here, notice we are keeping distance constant. We cannot have more than one independent variable. So right now our independent variable is charge. So notice I'm going from 1 positive, 2 positives to 3 to 4. My electrons again aren't changing. I'm keeping everything constant but my independent variable that I am changing. The dependent variable that I'm measuring then is that force of attraction. So what happens to my force of attraction as I increase the amount of positive charges here? It increases. This one kind of makes the most sense. As I add more magnets to one thing, it's going to attract that magnet even more regardless of how far away it is. So, next up, that periodic trend. Since we already looked at going up and down a column, we're now going to look at going from left to right in a row. So here we have sodium, aluminum, and chlorine, and they're all going to be in that third row on the periodic table. If you check that out, sodium is going to be on the far left, aluminum is going to be kind of towards the middle, and then chlorine is going to be on the far right. And so what happens as I go from left to right on the periodic table or across the row, the nuclear charge increases. That's kind of a fancy term, nuclear. What's in the nucleus? Protons and neutrons. And so that charge is increasing because I'm increasing the number of protons. Sodium has 11 protons, aluminum has 13 protons, and chlorine has 17. Where did I get those numbers? I looked at the atomic number at the top of those boxes. So sodium again has 11, where aluminum has 13. So aluminum has 2 more protons that are pulling even harder on that electron in the outer level. One thing I always have students ask me is, yeah, but there's more electrons for it to pull on. And that does have somewhat of an effect, but those protons are so much bigger than the electrons are that it overpowers that kind of increase. There are some deviations to this that you will look at in IB or AP chemistry, where there are some exceptions to things that happen when we do double up those electrons in those orbitals. But again, this relationship then, as I go across a row or period on the periodic table, I'm going to get a smaller atomic radius. I'm adding protons, so think about tug of war. If I had more people on one side, they're going to pull harder in on those electrons, and it's going to cause the radius to get smaller. And then we're going to have a larger ionization energy. The smaller an atom is, the higher the energy is, because it's going to take more energy to get rid of that electron because they are closer to that center, to that positive charge. They're holding on to them tighter. So, and then we can add to our arrows that were on our up-down. Now looking at our arrows that are going across. So again, atomic radius increases as I go from right to left. So these are going to be my biggest. So my biggest element is going to be francium over here because it is all the way over to the left and all the way at the bottom of our idea. We kind of don't really talk about the green ones down here. We're really only focusing on this first little rectangle area. So francium is going to be my biggest. Helium then going to be my smallest. So the other trend then is ionization energy. Which elements are going to have the highest ionization energy? Well, my noble gases for sure are going to have high ionization energies, and then fluorine is a really high ionization energy as well. It definitely does not want to lose an electron. It wants to gain an electron and be more like neon. So hopefully you can recognize the 2 different trends of radius increasing and ionization energy related to Coulomb's law. Next up, we are going to practice that. So with 3.3, you're going to practice through some different questions related to those atomic trends.